I want you to imagine, just for a second, that you have just taken delivery of a state-of-the-art supercomputer.
Oh, man. Okay.
Right. And we are not talking about, like, a high-end gaming rig here, or even a server rack for a mid-sized business.
Yeah, you mean the big stuff.
Exactly. We're talking about $100 million completely bleeding-edge marvel of human engineering. I mean,
Mhm.
the kind of machine that governments and international conglomerates literally fight over.
Right, something that takes up a whole room.
Exactly. So you plug it in, you start running your most complex calculations. Let's say you're modeling a totally new molecular structure for a breakthrough pharmaceutical, and you're feeling pretty good about the future.
As you should for $100 million.
Right. But then you get a tap on the shoulder, and the installation technician looks at you, clipboard in hand, and he says, by the way, every couple of hours, you're going to need to manually shut this entire system down.
Which is just wild.
Right. He says you'll need to open up the casing, take out a microscopic screwdriver, and manually adjust the internal screws and voltage dials.
Just unbelievable.
And when you ask why in the world you would have to do that to a $100 million machine, the technician casually replies, oh, well, because somebody closed a heavy door down the hallway,
Yeah.
and the acoustic vibrations threw the whole system out of whack.
I mean, it sounds completely absurd. If a company sold you a traditional server that operated like that, you would demand a refund immediately.
You'd send it right back.
Totally. It sounds like a sketch about some clunky, temperamental antique from like the 1950s where engineers were constantly swapping out blown vacuum tubes or something.
Yeah, you would absolutely send it back. But here is the massive paradigm shift we're exploring today in this deep dive. That absurd, completely frustrating scenario. That has actually been the daily, widely accepted reality of quantum computing.
It really has.
The most advanced mind-bending machines on the planet have functioned exactly like that up until this very moment. I mean, it's an open secret in the industry that we just don't talk about enough outside of academic circles.
Right, because we build these breathtakingly complex processors relying on the absolute frontiers of theoretical physics and materials engineering.
Yeah.
But they are so deeply fragile that they remain fundamentally impractical for sustained, real-world commercial use. We've basically been building Ferraris that can't drive more than a block without needing a full pit crew.
That is the perfect way to put it. But that era just ended. Which brings us to the formal mission statement for today's deep dive.
Let's hear it.
We are exploring a truly groundbreaking paper. This was published in the journal Nature on July 8, 2026. And it was authored by the team at Google Quantum AI.
Huge news.
Today, we're going to unpack exactly how Google completely eliminated the need for this quantum downtime. I mean, they didn't just build a better, more precise screwdriver.
No, they went way beyond that.
Right. They taught the machine to self-correct on the fly without ever stopping the computation using artificial intelligence.
And just to set the table for you listening, we are drawing entirely from a highly detailed source article that breaks down this specific Nature publication.
We have a lot of ground to cover.
A massive amount of incredibly dense ground. But the foundational framing you need to keep in mind is this isn't just a quantum hardware story.
Right.
This isn't just about dilution refrigerators and superconducting circuits. At its core, this is a story about what happens when world-class reinforcement learning AI collides head-on with quantum physics.
Oh, wow.
Yeah, it is the fusion of two completely different frontiers of human knowledge.
Okay, let's unpack this. Because to truly appreciate the elegance of the cure here, we really need to understand the underlying pathology of the disease.
Definitely.
Let's pivot from the broad, high-level overview and look closely at the physical problem plaguing these machines. We are talking about this multi-million-dollar antique problem. Why is this hardware so incredibly needy?
Well, it comes down to what the hardware actually is.
Right. And I know you listening probably understand the basic premise that qubits leverage superposition and entanglement rather than binary ones and zeros. So we can skip the basic computer science class.
Good call.
Let's talk about the physical architecture. Most of these leading machines, including Google's, use superconducting qubits, right? Specifically transwines. Why are they so volatile?
So the volatility is inherent to the physics of what a superconducting qubit actually is. A transmon qubit is essentially an artificial atom built out of superconducting circuits,
Okay.
specifically something called a Josephson junction. Now, To maintain its quantum state, it has to be kept at a temperature fractionally above absolute zero.
Which is why they have those massive dilution refrigerators.
Exactly. Because you are relying on incredibly delicate quantum states, the qubit is hypersensitive to literally any energy exchange with its surrounding environment. We call this decoherence.
Decoherence. And based on our sources, the list of things that cause decoherence is just staggering. I mean, the article details the specific environmental disruptors, and it's not just major anomalies like power grid surges.
Oh, not at all.
We are talking about microscopic temperature fluctuations inside the cryostat itself, ambient electromagnetic interference from the building's wiring.
Yeah, even just existing in a building is a problem.
Right. And even the natural, unavoidable physical aging and oxidation of the materials used to build the chip itself over a period of weeks.
I mean, it goes even deeper than that, actually. Going back to your opening scenario with the heavy laboratory door.
Oh, right, the door.
We're talking about microscopic acoustic vibrations traveling through the floorboards of the research facility. That tiny mechanical wave reaches the dilution refrigerator, subtly shifts the physical distances between components by fractions of a nanometer.
Fractions of a nanometer.
Yes, and that alters the magnetic flux. That microscopic shift is enough to change the optimal control parameters of a qubit. We call this systemic phenomenon drift.
Drift. Let's define drift operationally, just because it's so central to this whole paper. When we say the parameters drift, what physical dials are actually drifting?
Well, when you operate a quantum computer, you don't just type code and hit enter,
Not a normal keyboard setup.
No, you manipulate the qubits by firing highly calibrated microwave pulses at them. To perform a specific operation, say a quantum logic gate, you need a microwave pulse with a very specific frequency, amplitude, and an exact duration.
Okay, so it's a very precise burst of energy.
Exactly. If the environment changes even slightly due to that acoustic vibration, the resonant frequency of the artificial atom changes.
So the qubit's frequency shifts, but your machine is still firing the microwave pulse at the old frequency.
Precisely. You experience what physicists call a detuning error. Your control parameter, the microwave pulse, is no longer optimal for the current physical reality of the chip.
Wow.
The parameters have drifted away from their ideal settings, and suddenly your quantum gate operations start introducing massive errors into the calculation.
So the environment is just constantly whispering to the qubits. The qubits change their behavior in response, and the hardware's control parameters slowly fall out of sync.
That's a great way to put it.
Up until this Google Nature paper, what has been the accepted status quo for dealing with this drift? Because obviously, computations have been happening. People have been publishing papers for years. How have researchers been fighting this losing battle?
The traditional archaic solution is a labor-intensive process we can basically summarize as stop and recalibrate.
Stop and recalibrate.
Yeah. When the parameter drift becomes too severe, which you notice because the error rates of your calculations start climbing unacceptably high, the researchers have to physically pause the quantum computation.
Oh.
They stop the machine from running the algorithm.
They just halt the program mid-run.
They have to, because once you stop the primary computation, you then have to run a series of specific benchmark tests.
Like diagnostic.
Right. Specialized diagnostic routines, things like randomized benchmarking or measuring Rabi oscillations. And these are designed solely to figure out exactly how far the system has drifted.
Oh, I see.
Once the diagnostics map out the new physical state of the chip, human engineers, or sometimes classical optimization scripts mimicking human tuning methods, have to sit there and manually recalculate and adjust all those control parameters.
So they update the voltages?
They update the voltages, they shift the microwave frequencies, they recalibrate the coupling gates back to optimal baselines.
And only after all that manual labor is finished can they reboot the system and try to resume operations.
Assuming the state of the computation wasn't entirely lost during the downtime, which honestly is often the case.
So the F1 car analogy from our sources really is the best way to visualize this. It is literally like trying to win an ongoing Formula One endurance race, but the physical reality of your vehicle dictates that you have to completely stop your car on the track every 3 laps.
Right on the track.
Yeah, you pull over, have a pit crew completely disassemble and manually rebuild the engine to account for the wear and tear. And only then can you keep driving. You might have a car capable of hitting 250 miles per hour, but if you keep having to pull over to rebuild the engine, you are never going to win a long-distance race.
That analogy highlights the core frustration of the entire quantum engineering field. And we need to emphasize why this specific limitation matters so deeply for the broader future of the technology.
Yeah, why is this a deal breaker?
Well, If you are just a researcher running a short theoretical quantum algorithm that takes like 3 or 4 minutes to complete, this stop and start method is entirely workable.
Right, you can manage that.
You calibrate the machine in the morning, you run your quick 3-minute experiment, and you extract your data before the environmental drift has a chance to ruin the fidelity of the qubits.
It's like doing a quick quarter-mile drag race before the engine has a chance to overheat and fall apart.
That's a fair comparison. But the truly valuable quantum algorithms of the future, the legendary applications everyone is waiting for, are not drag races.
We're talking about the big stuff.
Exactly.
Yeah.
If we want to simulate complex molecular interactions to discover new life-saving drugs, or model global climate systems with unprecedented accuracy, or run Shor's algorithm to break RSA encryption,
Which is the holy grail.
right, those algorithms will not finish in 3 minutes. Based on our current understanding of quantum gate speeds, those calculations will need to run continuously, without interruption, for days or even weeks at a time.
And you simply cannot stop a week-long, highly entangled quantum calculation every few hours to tinker with the voltages.
We lose everything.
Right. If human engineers and classical scripts are way too slow to keep up with the drift, and stopping the machine entirely ruins the long-term computation anyway, it begs a massive, seemingly impossible question.
Yeah.
How do we tune the F1 engine while the car is still driving down the track at 200 miles per hour? I mean, we can't stop. The humans are too slow, so what do we do? Which brings us directly to Google's highly unconventional solution.
And this is where the Nature paper introduces the true hero of our story. To fix the engine while it's running, the Google Quantum AI team brought in an AI mechanic.
An AI mechanics.
Specifically, they utilized a reinforcement learning, or RL, AI agent.
Reinforcement learning. For you listening, this specific branch of AI might ring a bell, because this is the exact same fundamental technology paradigm that catapulted artificial intelligence into mainstream global consciousness a few years back.
Oh, absolutely.
This is the underlying tech architecture that allowed Google DeepMind's AlphaGo to famously and somewhat shockingly defeat the human world champion Lee Sedol in the incredibly complex board game of Go.
It is the exact same family of algorithms, and to ground it even further in today's tech landscape, it's also the core idea behind how modern large language models are fine-tuned for human interaction.
Oh, right.
The RLHF that you constantly hear associated with ChatGPT, that stands for reinforcement learning from human feedback.
So it's everywhere now.
It is. At its absolute theoretical core, reinforcement learning is about an AI agent learning the best possible strategy to achieve a goal. And not by being programmed with a static human-written rulebook, but through repeated dynamic interaction with a complex environment.
It's trial and error on a massive mathematical scale.
Essentially, yes. The RL agent takes an action in the environment, it observes the resulting change, it receives a mathematical reward if the outcome was good, or a penalty if the outcome was bad.
Sort of like training a dog with treats.
Exactly like that. And then it subtly adjusts its internal policy for future actions accordingly.
Right. So we have this incredibly powerful, adaptable AI tool that excels at finding strategies in messy environments. But to understand how Google successfully applied it here to quantum hardware, we have to look at the ingenious connection they made.
Because they didn't just plug AlphaGo into a quantum chip.
Right. They married reinforcement learning with a completely different scientific concept called quantum error correction, or QEC. I want to spend some real time on this because it's the bridge between the two sciences.
Yeah.
Break down QEC for us. What is the actual mechanical baseline concept there?
Quantum error correction is arguably the most important foundational theory in the field right now. It is the theoretical blueprint for how we plan to build highly reliable, large-scale quantum computers out of inherently unreliable, noisy physical parts.
Okay.
Because individual physical qubits are so fragile, as we just discussed, QEC protects the actual computational information by encoding one single logical qubit across a large group of multiple physical qubits.
Okay, I want to make sure we don't lose anyone here.
Yeah.
The physical qubit is the actual piece of hardware, right? The superconducting loop on the chip.
Yes.
And the logical qubit is the piece of mathematical information. So it's about redundancy. I always think of it like having 10 people memorize a phone number instead of just one person.
That's a great way to think about it.
Right, because if the one person forgets a digit, the information is lost forever. But if 10 people memorize it, and one person forgets a digit, the other 9 can compare notes, spot the error, and correct the 10th person.
That's a highly effective way to visualize the broad concept. In practice, QEC algorithms are constantly, relentlessly running in the background of a quantum computer.
Just checking the math.
Exactly. They are constantly measuring a subset of these physical qubits, often called ancilla, or measure qubits, to check the parity of the system. The algorithm is constantly asking, where did something go wrong? Did a bit flip happen here? Did a phase shift happen there?
Wow.
And when it detects an anomaly, it generates a steady stream of data called syndromes, which are basically error detection signals.
So it's constantly scanning the system and flagging mistakes. But the source material highlights a massive, almost tragic irony here. It's the problem hidden within the solution.
It really is.
QEC is supposed to be the immune system that fixes the errors, but QEC itself relies on those physical control parameters we talked about earlier, right?
That is the paradox that has stalled the industry. To run quantum error correction, to constantly measure those ancilla qubits without collapsing the delicate quantum state of the actual data, you have to fire microwave pulses at exact amplitudes.
Oh, so the measuring itself uses the same fragile tools.
Exactly. You have to open coupling gates for exact nanosecond durations. You have to tune the frequencies with microscopic precision. So if that heavy lab door closes and the environment causes the physical parameters to drift, the error correction mechanism itself starts misfiring.
Like guard dogs fall asleep, or worse, they start barking at the wrong things.
Exactly. When the parameters drift, the QEC starts generating faulty syndromes. It starts trying to correct errors that don't exist, or it ignores errors that are actively destroying your calculation.
Which is a nightmare.
It is. And the traditional response, as we covered, was to stop the machine, halt the QEC, and manually recalibrate all those parameters. But Google's stroke of genius in this Nature paper was looking at this entire messy, frustrating process from a completely inverted angle.
They flipped it on its head.
They did. They realized that the QEC process, even when it's struggling against drift, is naturally generating a continuous, massive stream of error detection signals.
It's constantly screaming, I found a mistake, the parity is wrong, something flipped.
Right. And the Google team thought, what if, instead of viewing those error signals as a reason to stop the machine and bring in the human engineers, we take those continuous error signals and feed them directly to our reinforcement learning AI agent?
Oh, wow.
What if those error signals become the mathematical reward and penalty feedback for the AI?
Okay, I have to jump in and push back on this, because when I was reading the supplementary materials for this paper, this specific part sounded completely counterintuitive to me.
Oh, for sure.
I mean, think about it logically. If the system's physical parameters are already actively drifting, and the QEC guard dogs are failing and generating messy, inaccurate syndromes, wouldn't feeding its own real-time degraded error signals back to an AI just create a catastrophic feedback loop?
It sounds like it would.
You are basically feeding an AI garbage data about a drifting system and asking it to fix things. How does the AI actually learn anything useful from that noisy chaos? Doesn't it just amplify the errors?
That is a brilliant challenge, and honestly, it is the exact crux of why this paper took so long to peer review and why it ultimately landed in Nature. The answer lies in the specific algorithm the AI uses.
Okay, lay it on me.
The RL agent doesn't just passively sit there listening to the noisy error signals and guessing what to do. It utilizes a highly sophisticated algorithm called proximal policy optimization, or PPO.
PPO, right.
The AI actively, mathematically probes the chaos. During every training round, while the quantum computer is actively running its normal operations, the AI agent reaches in and adds tiny, intentional, completely random perturbations to the control parameter.
Wait, it purposely messes with the dials. The system is already unstable, and the AI actively adds more instability.
It does, but we are talking about microscopic, highly controlled mathematical nudges. It nudges a voltage up by a fraction of a percent. It shifts a microwave frequency by a hair. And then, crucially, it closely watches how the continuous stream of error signals coming from the QEC change in response to those tiny intentional nudges. By doing this thousands and thousands of times a second across the chip, the AI calculates what we call in machine learning gradients.
Gradients, okay, let's ground that term. So it's essentially feeling around in the dark to see which way is up.
That's a great physical intuition for it. Imagine you are blindfolded on a bumpy, highly irregular hillside, and your only goal is to find the lowest possible point in the valley.
Right.
You can't see the landscape, so you tap your foot slightly in every direction around you. If tapping your foot forward feels like it goes slightly downhill, that's a positive gradient toward your goal, so you take a small step forward.
Makes sense.
If tapping to the left goes uphill, that's a negative gradient, so you avoid that direction. The PPO algorithm does the exact same thing with the quantum control parameters in a high-dimensional mathematical space.
Oh, wow.
It calculates the gradients of the QEC error signals to figure out which exact direction to turn all the dials to minimize the overall error rate.
So it subtly, continuously adjusts the probability distribution of the parameters on the fly, constantly chasing that downhill gradient toward optimal stability.
Exactly.
And the key takeaway here, the absolute game changer that makes this a milestone in physics, is that during this entire optimization process, the processor never stops computing, not even for a millisecond.
Never stops.
It just continues running its normal required error correction cycles while this RL agent acts as a sort of benevolent ghost in the machine, just quietly tuning the knobs, tightening the screws, and shifting the frequencies in the background, adapting to the environmental drift in real time.
Returning to our earlier analogy, the F1 car never leaves the track.
Right.
The AI mechanic is basically strapped to the hood of the car, feeling the vibrations of the engine, and constantly tuning the fuel-to-air mixture with a microscopic wrench while the car is sustaining 200 miles per hour indefinitely.
It is an unbelievably elegant theory. I mean, the math is beautiful, but theory is one thing, and theoretical physics is littered with beautiful ideas that fall apart in the lab.
Oh, definitely.
I want to know what actually happened when this theoretical AI ghost was unleashed on physical, bleeding-edge quantum hardware. Let's talk about the physical battleground where this experiment actually went down.
The physical battleground chosen for this paper was Google's Willow superconducting processor.
Willow, for you listening, we really need to contextualize what a beast this specific processor is in the history of the field.
Yeah.
We have to remember Willow's pedigree.
It's a legend.
This chip was first announced to the world in late 2024. And when it debuted, it made massive global headlines. It completed a specific computational benchmark task in standard time that Google claims would take a classical supercomputer roughly 10 to the 25th power years to complete.
It was a monumental achievement in raw computational supremacy and speed. But this new experiment, detailed in the 2026 paper and led by first author Volodymyr Sivak, was a complete pivot in their research goals.
They shifted focus entirely.
They weren't trying to break another speed record to impress the press. This experiment was entirely about stability. It was about seeing if they could finally tame the beast they had built.
And the scale of this optimization challenge is hard to overstate. When we talk about parameters, the RL agent wasn't just managing 2 or 3 dials like adjusting the treble and bass on a stereo.
Oh, no.
According to the source, the AI was tasked with managing over 1,000 unique control parameters simultaneously.
We are talking about intricately coordinating the microwave pulse amplitudes, the precise superconducting qubit frequencies, and the exact physical strengths of the coupling gates.
All at the same time.
All at once, across a highly fragile, deeply entangled quantum matrix.
I was trying to think of a good way to visualize this. Earlier, we talked about a spaceship with 1,000 joysticks, but that doesn't really capture how everything interacts, you know?
It's too simple.
Right. Instead of joysticks, I was thinking about it like this. Imagine trying to manually tune a 1,000-piece symphony orchestra. But you aren't just tuning each violin in a vacuum. The system is so coupled that if you tighten the strings on the cellos, it subtly changes the resonant acoustic frequency of the wooden stage they're sitting on.
I like this.
And then that slightly alters how the brass section sounds on the other side of the hall. Every single adjustment impacts everything else in the room. You have to tune all 1,000 instruments simultaneously while the orchestra is actively playing a Beethoven symphony.
Yes.
It is a task that has far, far exceeded the capacity of any human engineer or any classical linear human-written script to optimize manually.
That is a phenomenal analogy because it perfectly highlights the concept of nonlinear crosstalk.
Crosstalk, right.
In a quantum processor, qubits are physically and electromagnetically coupled to each other. Adjusting the flux bias on one qubit often unintentionally shifts the frequency of its neighbor. Humans struggle to map out those complex, multivariable interactions.
Our brains just can't track it.
Which is exactly why the results they recorded when they finally turned the AI loose on the Willow chip are so staggering. Let's look at the data deep dive from the paper. First, the researchers artificially introduced hardware drift.
They broke it on purpose.
They basically intentionally messed with the environment to degrade the system and force the AI to react. In the face of that artificial aggressive drift, The autonomous RL agent stepped in and boosted the logical error rate stability of the system by 2.4 times compared to baseline.
A massive 240% jump in computational stability just from the AI tweaking the dials on its own in the background.
Yes, and it gets better. When they co-optimized the RL agent to work in tandem with a classical decoding algorithm, the software that interprets the final output, that stability jump, leaped to a 3.5 times improvement.
Wow.
But the biggest shock, the data point that really stunned the field and got everyone talking, was what happened when they pitted the AI directly against the human experts.
It is the man versus machine moment.
It really is. The researchers had their senior human quantum engineers painstakingly perfectly calibrate the Willow machine using the absolute best traditional time-consuming stop and recalibrate methods available to the industry.
The old way.
Yeah, they used every trick they knew to get the chip as stable and error-free as humanly possible. Then they unleashed the RL agent on that supposedly perfectly calibrated system.
Yeah, what happened?
The AI stepped in, observed the complex crosstalk that the humans couldn't map, found hidden inefficiencies in the high-dimensional parameter space, and suppressed the logical error rate by an additional 20%.
It completely shattered the traditional ceiling of human calibration. I mean, the human engineers thought the engine was perfectly tuned to its absolute physical limit, and the AI mechanic stepped in and found 20% more horsepower just by listening to the microscopic vibrations and tweaking the couple parameters in ways a human brain couldn't even visualize.
Exactly.
How exactly did it beat them?
Well, it comes back to your orchestra analogy. Human engineers tend to optimize parameters sequentially. They tune qubit A, then they tune qubit B, then they try to adjust the coupler between them.
Very linear.
Right. But the RL agent, processing all the gradients simultaneously, found global minima in the optimization landscape. It realized that slightly detuning qubit A from its perfect individual state actually reduced the overall crosstalk across a block of 10 qubits, leading to a much better systemic outcome.
What's fascinating here is the specific record-breaking numbers they achieved. And before we just throw numbers out, let's unpack the jargon, because the paper heavily relies on these terms.
It can get dense.
In the complex world of quantum metrics, they tested this AI on 2 different error correction layouts. First, they cite a distance 7 surface code, where they achieved a logical error rate of 7.72 times 10 to the negative 4th power per cycle.
Right.
And second, for a distance 5 color code, it reached 8.19 times 10 to the negative 3rd power. For those of us who follow the field but aren't building these chips in our garages, what physically is a distance 7 surface code, and why do those scientific notation numbers matter?
Okay, so a surface code is a specific geometric layout of qubits on a 2D chip. Imagine a checkerboard. The black squares are your actual data qubits holding the information, and the white squares are your ancilla measure qubits checking for errors.
Okay, got the visual.
The distance refers to the size of that grid, and crucially, how many physical errors the system can tolerate before the logical information is corrupted. The mathematical rule is that a code of distance d can tolerate d minus 1 divided by 2 errors.
Okay, so if it's a distance 7 code, 7 minus 1 is 6, divided by 2 is 3.
You got it.
So a distance 7 code can suffer 3 physical errors simultaneously anywhere on the grid, and the system can still successfully correct it.
Precisely. And building a functional distance 7 code on superconducting hardware is incredibly difficult due to the massive number of coupled qubits required. So achieving an error rate of 7.72 times 10 to the negative 4th, which is basically 0.00007 errors per cycle, is monumental.
Why is that the magic number?
Because these are the absolute best publicly reported scores ever achieved for superconducting processors. To give you context on the pace of progress, Google's own benchmark from just late 2024 for surface code logical error rates was still up in the 10 to the negative 3rd range.
Oh, wow.
By applying the single RL software architecture, they shrank their own previous state-of-the-art error rate by nearly 30% without changing the physical chip at all.
It is a massive leap forward in fidelity, powered entirely by software.
Yeah.
Okay, we absolutely have to celebrate hitting a world record on 1,000 parameters. It's a milestone.
Huge milestone.
But I have to play devil's advocate here, because there is a glaring issue that immediately jumps out to me when thinking about the commercial future of this technology.
Let's hear it.
1,000 parameters is a lot for a lab experiment today. But a truly useful, fault-tolerant quantum computer, the kind we discussed earlier that models the climate or breaks encryption, It's not going to have 1,000 parameters.
Not even close.
It's going to require thousands of logical qubits, which means millions of physical qubits, which means tens of millions of control parameters.
That is the ultimate scaling cliff the industry is facing.
So does this AI mechanic actually scale? If we give it 1,000,000 interrelated joysticks or 1,000,000 instruments in the orchestra, does the classical compute overhead required to run this AI ghost in the machine eventually get overwhelmed and crash the whole ship?
This was the exact existential question the Google team knew they had to answer in this paper to prove this wasn't just a neat parlor trick on a small chip.
Right, they had to prove it scales.
To address the scaling question, since a 1,000,000 qubit chip doesn't exist yet, they ran a massive, highly detailed numerical simulation of a theoretical distance 15 surface code. This is a drastically larger, more complex quantum architecture. And this specific simulation involved coordinating approximately 40,000 control parameters simultaneously.
So they artificially scaled the problem up 40 times the size of the physical Willow experiment to see if the AI would break.
Exactly. And this brings us to what I consider the absolute aha moment of the entire paper for quantum researchers.
What did they find?
The team actively measured the RLAI's convergence speed. In machine learning, convergence speed is the metric of how fast the AI learns the environment, maps the gradients, and successfully stabilizes the system.
Right.
And what they discovered is that the AI's convergence speed is completely, entirely independent of the quantum system's overall size.
Wait, independent, meaning it didn't slow down at all.
It didn't slow down. Facing 40,000 parameters mathematically took the AI no longer to learn and stabilize than facing 1,000 parameters.
You're saying the AI convergence speed is independent of size. But hold on, let me push back on this, because the quantum system is local, sure, but the RL agent is running on a classical computer. If you have 40,000 parameters, the state space the AI has to process is astronomically larger. Doesn't the classical compute power required to calculate those gradients in real time become the new bottleneck?
It seems like it would.
Right. If you scale this to 1,000,000 qubits, aren't you just trading a quantum hardware problem for a classical supercomputing problem? How does the AI just brush off a 40x increase in complexity without a massive classical compute lag?
That is a highly sophisticated challenge, and the answer lies in a deep principle in quantum physics called locality, paired with a decentralized approach to the AI architecture.
Locality, good.
Quantum error correction has a fundamentally local structure. Imagine the surface code checkerboard as a massive grid of city streets. A physical error on a qubit typically only propagates to its immediate neighbors.
Just the surrounding block.
Exactly. If the AI agent tweaks one specific parameter, let's say fixing the timing of a traffic light at one specific intersection in the grid, it mostly only affects the error detection syndromes in that immediate local neighborhood of qubits.
It doesn't reroute the traffic for the entire country.
Exactly. A parameter change on the far left side of the chip doesn't wildly disrupt the physical reality on the far right side of the chip. Because of this physical locality, the classical reinforcement learning agent isn't actually forced to solve one massive, tangled, 40,000 variable equation all at once in a single central processor.
Oh, I see.
The researchers designed the reward functions to be local. The AI is essentially deploying decentralized policies, simultaneously solving thousands of tiny, localized optimization problems that just happen to be sharing the same physical chip. The classical processing can be parallelized because the quantum physics is localized.
So what does this all mean for the roadmap of quantum computing?
It implies that the scaling bottleneck for control systems is broken. Facing 40,000 parameters is mathematically no harder for this decentralized AI architecture than facing 1,000.
That is wild.
It implies that this real-time, RL-driven self-correction method is fundamentally ready for the massive, large-scale, fault-tolerant quantum computers of the future. We don't have to wait for a breakthrough in classical processing to manage the quantum chips of tomorrow. The software architecture is officially ready for the hardware to catch up.
That is thrilling to hear. But we do need a crucial reality check here, right? We shouldn't leave the listener with the impression that we solved quantum computing entirely today and we'll have desktop quantum PCs next year.
We definitely haven't, and we need to temper the excitement with the harsh realities of the physics that remain unsolved. This Nature paper focuses specifically on what we call quantum memory.
Quantum memory.
The entire Willow experiment was about keeping a single logical qubit stable over time, preserving its internal state against the degrading environment.
It's about holding the memory intact, not manipulating it.
Right. Preserving a memory in a static state is a prerequisite. but it is not the same as executing complex, universal quantum logic gate operations between multiple logical qubits.
We're not running algorithms yet.
We aren't actively running Shor's algorithm here. We are just keeping the lights on and the data pure. We still face monumental engineering hurdles ahead. We have to fundamentally improve the raw coherence times of the physical qubits themselves. We have to dramatically improve the fidelity of logic gates during active computations.
There's still so much to do.
And we still have to figure out the sheer physical engineering nightmare of building cryostats large enough to house these massive surface codes.
So we haven't crossed the finish line by any means.
Not at all. But I want to read a highly poignant quote from the concluding summary of the paper's authors because it fundamentally reframes the entire journey of the industry.
Okay, let's hear it.
They wrote, "The path to fault tolerance is built not just on better hardware, but on smarter control."
Smarter control.
Yes. For decades, the entire field operated under the assumption that the only viable way forward was to build hardware so perfect, so isolated, and so physically pristine that errors simply wouldn't happen in the first place.
Which feels impossible.
The Google team has essentially demolished a massive roadblock that everyone thought had to be carefully, expensively driven around. They proved that you can have slightly noisy, imperfect hardware as long as you have fiercely intelligent, adaptive software managing it in real time.
And we know this isn't just corporate PR hype because of the extreme rigor of the science involved. I want to point out a meta detail about the publication timeline that our source material highlights, which I think is fascinating.
Oh, the timeline.
This paper was originally submitted to the pre-print server, Archiver, back in November of 2025, but it didn't officially publish in Nature until July 8th, 2026.
That is an 8-month gap between public submission and official peer-reviewed publication.
8 months. And for you listening, if you aren't in academia, you have to understand the notorious uncompromising strictness of Nature reviewers, especially in a heavily scrutinized, hype-filled field like quantum computing.
They do not mess around.
They don't just read the paper, check the grammar, and give it a thumbs up. They demand raw access to the data. They demand mathematical clarifications. They relentlessly attack the methodology to ensure the claims hold up against every possible alternative explanation.
It is a brutal crucible of peer review.
Surviving an 8-month gauntlet with Nature's reviewers proves the absolute undeniable solidity of this work. This isn't theoretical wishful thinking. This is rock-solid, verified science.
Absolutely.
But taking a step back from the peer review process and the physics itself, there's a fascinating macro observation here that the source material touches on. This historic, paradigm-shifting breakthrough in quantum hardware stability didn't come from a pure quantum hardware startup.
Right.
It didn't come from a legacy superconductor manufacturing firm. It came from Google. And that implies a much deeper structural pattern about where scientific breakthroughs are coming from today, which leads us perfectly into the macro implications of this paper.
It's the most important question to ask. Why Google? Why did the company originally famous for a search engine manage to solve the quantum hardware bottleneck that has stymied dedicated physics labs for years?
Here's where it gets really interesting. Google is leveraging its massive, unparalleled historical pedigree in artificial intelligence. Think about their track record over the last decade.
It's unmatched.
They built AlphaGo to master complex strategy. They built AlphaFold, which practically overnight solved the 50-year-old grand challenge of protein folding in biology. They invented the transformer architecture, the T in ChatGPT, that literally powers every modern language model today.
Right, they laid the foundation.
They designed custom TPU chips to process AI math at a global scale.
They have systematically built the most advanced interdisciplinary AI toolset in human history. And what we are witnessing in this Nature paper is the maturation of what we might call the AI spillover effect.
The AI spillover effect. Unpack the mechanics of that for us.
Google isn't just doing quantum physics in a vacuum, isolated in a physics department. They are looking at complex, incredibly messy physical world problems like the decoherence and parameter drift in a quantum chip, or the thermodynamic folding of a protein chain. And they are realizing that these are just data problems.
Oh, I see.
They are translating those physical realities into high-dimensional mathematical optimization problems. And once a problem is translated into math, they can unleash their world-class AI toolset on it.
So they took a thorny physics problem, disguised it as a mathematical optimization landscape, and hit it with an AI hammer.
That's a great way to summarize it. Applying proximal policy optimization to quantum error correction is essentially just taking the exact same algorithmic toolbox they used to beat Lee Sedol at Go and applying it to a new physical game board.
Wow.
And this AI capability spillover might actually be the single most important technological trend of this entire decade. It might ultimately be even more impactful than the quantum hardware itself.
Because it implies that whoever holds the best AI algorithms holds the skeleton key to unlocking every other scientific discipline. Biology, chemistry, material science, quantum physics. AI is becoming the universal translator for scientific breakthroughs.
And that leads us to a vital global context explicitly mentioned in our source material. When we look at the geopolitical landscape of quantum computing, we have to look closely at the intersection of these two specific fields.
Right.
And we must approach this objectively, looking strictly at the public data, patents, and published achievements. When it comes to pure physical quantum hardware, the global race is incredibly tight. China, for example, is highly competitive and arguably not behind at all in physical hardware development.
The source notes they have made massive documented strides in superconducting advances. They have the Juzhang series of optical quantum computers, which have repeatedly broken their own computation records.
Very impressive machines.
And various Chinese academic teams have published significant, highly successful recent experiments regarding the physical implementation of surface codes.
Physically, they can absolutely build the machines. They have the foundries and the physics expertise. But this Google Nature paper highlights a new, highly specific dividing line.
What's the line?
When you look at the exact intersection of quantum plus AI, the deep functional fusion of these two domains to manage hardware China has very few public achievements in that specific cross-section.
Why is that? If they clearly have the hardware capability, and they certainly have world-class AI researchers working on language models and computer vision, why does there appear to be a gap at the intersection?
If we connect this to the bigger picture, it fundamentally comes down to a highly specific structural talent bottleneck.
Talent bottleneck.
Let's look closely at the team at Google that published this paper, including the lead author, Volodymyr Sivak. This team is packed with people who possess deep dual backgrounds. They aren't just theoretical physicists who dabble in Python, and they aren't just AI software engineers who read a Wikipedia article on qubits. They are truly fluent in both. They hold deep academic expertise in both quantum mechanical physics and reinforcement learning architectures.
They're completely bilingual in physics and AI.
Exactly. And according to the analysis of the current landscape provided in our sources, this specific cross-disciplinary talent structure, entire research teams of bilingual researchers housed in the same labs, is currently quite rare in China's domestic ecosystem.
Oh, I see.
They have brilliant physicists and they have brilliant AI scientists, but the deep structural integration of the two disciplines at the highest levels of corporate and academic research is lagging behind the interdisciplinary melting pot that Google has built.
Which sets up an absolutely fascinating dynamic for the future of this technological race over the next decade.
It really does, because if this Google paper proves anything to the broader scientific community, it is that the second half of the quantum computing race is no longer just about who can build the coldest, most isolated, perfectly pristine physical hardware.
The hardware race is shifting.
The pure hardware race is showing signs of plateauing. The second half of the race is entirely about software. It is about the ability to manage, stabilize, and extract usable value from noisy quantum systems using artificial intelligence.
And if advanced software management is the new finish line, then this specific educational and talent gap, the ability to cultivate, fund, and retain researchers who natively think in both qubits and gradients, that is going to become the new ultimate dividing line between global competitors.
It is a profound shift in how nations, universities, and corporations will need to structure their research divisions moving forward. You can't silo your AI team in one building and your quantum team in another building anymore. They have to share the same laboratory, the same language, and the same goals.
It's an incredible realization. Let's briefly recap this unbelievable journey we've been on today. We started with the frustrating, almost comical reality of quantum downtime, multi-million-dollar machines constantly needing manual human recalibration just because the environment whispered to them. But the team at Google Quantum AI proved that manual downtime is effectively dead.
They took reinforcement learning, the same fundamental AI architecture that masters complex board games, and taught it to interpret the messy error signals of a quantum processor in real time, calculating gradients and tuning the physical parameters on the fly without ever stopping the computation.
And not only did it work, It found global optimizations that outperformed the very human engineers who built the machine by 20%. And then through the magic of local physics, they proved that this decentralized AI mechanic doesn't even break a sweat when scaling up to 40,000 parameters. It is ready for the big leagues of fault tolerance.
And it all stems from Google's deep historical pedigree in AI, proving that the future of quantum physics relies heavily on cross-disciplinary AI and physics talent, setting up a new paradigm in the global technology race.
Which brings me back to you, the listener. Why should you care about superconducting surface codes and AI gradients? Because this deep dive proves a fundamental truth about the world we live in right now. The biggest, most earth-shattering leaps in human knowledge aren't happening deep inside the isolated echo chamber of a single discipline.
They're really not.
They are happening in the collisions. They are happening when the AI developer accidentally bumps into the quantum physicist in the hallway and they realize they are working on the exact same optimization problem from two different angles. It is a powerful reminder to always look for connections outside your immediate area of expertise. Your biggest breakthrough might just be hiding in someone else's field.
I think that is the perfect takeaway for today, but I do want to leave you with one last provocative thought to mull over long after we sign off.
Let's hear it.
In this experiment, an AI agent learned how to manage and stabilize a quantum computer 20% better than the human experts who physically built it. The AI understood the subtle hidden relationships and crosstalk between the hardware components better than its own creators did.
Right.
So what happens when we eventually ask an AI not just to manage the existing chip, but to design the physical layout of the next quantum processor from scratch, based entirely on its own alien, deeply mathematical understanding of how errors actually propagate?
The mind boggles. A machine designed by AI, stabilized by AI, to calculate the deepest secrets of the universe. It is a brave new world, and we are just standing on the threshold. Thank you for joining us on this deep dive into the Nature paper. Keep questioning the status quo, keep looking for those unexpected connections across disciplines, and keep exploring. We'll catch you on the next deep dive.